This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. There won't be as much show and tell as last lecture. That was to try and give a context for the stuff to come today. Alrighty. Last time, I hope that everyone was had a common understanding of clearance, interference, and transition fits. And last time I went through this little process of maximum and minimum clearance because it's always about having a fit. Some way or other, one object and another object come together to create a fit, whether it be, in this case, clearance between a minimum and a maximum with an associated hole and shaft tolerance, whether it be an interference where we're going to have a minimum interference and a maximum interference. So we're always looking for those extremes, least to worst and least to worst. We don't really care much about the smallest hole and the smallest shaft. Biggest, smallest, smallest, biggest is what we're always after. With an associated minimum and maximum for the hole, minimum and maximum for the shaft. And tolerance. Now these T, tolerance numbers, they come from tables. We will nominate a fit from there's a lovely little guide that I'll show you in a sec that provides us with an idea of what a suitable fit is for the application. And that'll be enough for this introductory class. And then we go to tables and we can find out what the numbers are that will provide us with a reasonable size tolerance rectangle or tolerance height for our manufacturing range. And then for transition, you've got a transition when you go biggest hole, smallest shaft, you've got a clearance, then biggest shaft, smallest hole, you've got an interference. So it's somewhere in that transition zone. And I was playing around with my brass shafts with my one brass hole last time. And by the by, what I've produced over there, and I'm sorry, I could have done this, but I forgot. All that cross-hatching there is an important thing compared to a solid block. We've got our cross-hatching for our hole, which is that tolerance, and in a bit of grey, shaded solid, is our tolerance for our shaft. And as I've said before, the height is super duper critical, is everything. The width of these rectangles doesn't matter. It's just about visualising what's going on. And hopefully, when I put the two rectangles together, I cut and pasted those two lines, the orange and the purple, and you hopefully get a bit of a clue about what we're going for. Transition fits, if I'm in the mood in an exam, are always the hard one, to be able to produce a transition fit deviation diagram. Call me. And again, tolerance of hole, tolerance of shaft from a standard based on a process that we'll go through in a sec. And as I've said, convention is that we have a cross-hatching for holes and a solid tolerance zone for shafts. Now, this is out of a standard, and what we're going for here is the idea of base. when we've got, like, whatever it might be, 10, 50, 100 millimetres is the basic size of the shaft and the hole. That's what I've got up there in the green dashy line. It's always, you know, when we're designing, we don't want to make things any more complex than it needs to be. And up on the screen, we've got this idea of the hole being the basis or the starting point for our tolerance process. So we'll have somewhere a capital H. Have I got it? Can't see it, but I'll be talking about it in a sec. Excuse me. And, oh, there it is there, for the hole. And that cross-hatched rectangle is representing, you know, the lowest limit and the upper limit for the hole. And these solid rectangles going up and up and up are equivalent clearance for, shaft, tolerance, rectangle for a clearance, transition or interference. Now, clearance, the shaft's tolerance is always less than. It always fits in the hole easily. Transition, sometimes not, sometimes yes, depending on, you know, the batch. And interference, the shaft and the hole will always interfere. Now, just for the sake to visualise, what's up on the screen now is essentially a visualisation of the top image. We only have the one hole. Yeah, I know this is a ring, but all we're worried about is the feature in the middle, the hole. And that hole is, you know, I could, as I played around with last time, I could put verniers and calipers on that hole and get a measure for that hole diameter, and even do it a few times, get a very accurate measure. But if we're in production and we're producing thousands or hundreds of thousands of them, we're going to get a range. And if that inside hole diameter is going to be within this zone, no less than whatever that is, let's say it's 10 millimetres, no less than 10 millimetres, but it can be a little bit bigger. The hole can be 10.1 millimetre diameter. Well, that's what that cross-hatching is showing. The shafts, by comparison, there's only 3, but imagine we've got 1,000 of each of those, clearance, transition or interference shafts. Each and every one of those shafts, I'll just pretend that this is the clearance. So it goes in pretty easily. Now, if I had thousands of shafts, their diameters would all be slightly less than that 10 millimetres I was talking about. It might be 9.95 to 9.98 or something, but they'll always fit in. For the transition, which is this one, now this one fits in just, which implies that the actual diameter of the shaft I'm playing with is somewhere there. If it was bigger within the tolerance range available, let's say that's 9.9 to 10.2, if I couldn't fit this particular shaft in, well then we're closer to the 10.2 than the 9.9. Literal diameter for that particular shaft. But the thousands and thousands that might be produced all have to lie within that range. And lastly, which I can't really demonstrate as easily because it doesn't fit in at all, the interference fit is as per what's up there. Every dimension, every measured dimension of the interference fit shaft will have a diameter, let's say, whatever I said before, 10 to 10.2, 10.3 to 10.4 or 5. Their diameter is always bigger. And that's essentially what that chart is showing. Hole base. What that's saying is that one of the dimensions of the hole is at a 0 point, just to make life easy. Everything's not some fancy, micron-based number. We can go the other way, and instead of what I was just showing, I could have had 3 holes and 1 shaft, 1 clearance hole, one transition hole, one interference hole, and they're the three tolerances associated with that, with one shaft sizing with a base dimension associated with the exact value we're looking for the dimension. So the zero line, if I was just talking about 10 millimetres, well, the zero line would be 10. And given that that solid line is going below 10, minimum diameter 9.9, 9.8. 9.9 up to 10. No greater than 10, or else the manufactured component is outside of the design tolerance. It fails the design tolerance test. So holes, shafts, and all we're looking at now are the those little tolerance zones. And just in case, I'm going to do a lot of flicking right now, just so everyone, because some students really struggle with this. This is the slide. When I'm showing you those little rectangles, always think about that little deviation diagram, work in progress, and that's a little tolerance rectangle, to give an idea of the bigger to the smaller as an upper and lower limit. That's what that rectangle is representing. There's a lot of them coming. And repeat, crosshatch for holes, solid for shafts. One more thing, and this is for the, what I always like to think about this stuff in terms of the geometry. I focus on the geometry. It sets me free from having to deal with numbers. I will get the numbers, put them on a diagram, reasonably well scaled, and then I've got a visualisation. And DP4, I'm asking you to do the same sort of thing. But I'm very aware that some students think better in terms of equations, and they do exist. So with all those preceding development images I showed, and I had Cmax and Imax and Cmin and Imin, and the tolerance for the hole, tolerance for the shaft, clearance max minus clearance min. There's a whole heap of equivalent equations there that provide the same kind of outcome as what the graphical representation can provide. But again, I would ask that you focus on the geometry and do a check with the maths. Ditto with the interference, and the same thing with the transition, except it's the hardest of all. Here we've got interference max, interference min. I've told you about how we never had such a thing as a negative. This is geometry. We're in three-dimensional space. It's always positive. We don't go negative. If you do get a negative, you've got to think, well, what does that correspond to? Like a negative clearance corresponds to an interference. It's as simple as that. It's not as if you can't just leave it as, oh, we've got a negative clearance on this. There's my answer. Sorry, but that's not responding logically to what we're talking about here. And by the way, I've just repeated that. Don't forget that this is all about, this tolerance zone is all about, we're producing thousands and tens of thousands of the same part, and we're going to get a range of sizing. And that range of sizing, we would hope, have its mean in the middle of that rectangle, and we move out in a 6 sigma style, where as we get towards the extremes, we get very few components. And I talked a little bit about that in the first lecture, the statistics of manufacture. Okay. Questions? I will answer these questions, of course. The whole lower deviation is set at the 0 point, or the base dimension, when we've got a whole basis fit. There's an implication of that for manufacture. We can do the shaft basis fit as well, and we tend to have the shaft upper deviation as 0. So capital H, lowercase h will have a capital H 0 or a lowercase h 0 for one or the other. And the significance. Whole base fits are useful for us. I'll go back to the model I brought in. with this simple little toy, you can imagine not terribly hard to get, Gary or Octay or Justin down the workshop to make that for me. They drill that out. But imagine if it, for a production setting, and maybe that hole is 10 times as deep. How do we get in there to manufacture it easily? When you've got an internal surface that we're trying to manufacture, especially when we're trying to do it with precision, it's a lot harder to get inside to get that precision than to be on the outside, as with the shafts. That is the reason that manufacturing types have told me, that we think that fixed tools are cheaper. So the idea of all these things, just a twist drill, a broach or a reamer, drilling the hole out, they are cheap components that we'll just use hopefully once reasonably well. We don't want to then do subsequent manufacturing tasks to get even more precision in that hole if we don't have to, because it's so much easier to, I'll go forward a slide, to do that than to get lathes and other external surface manufacturing systems. A lathe is really easy. Some of you have got more advanced knowledge of CNC machines and 5-axis mills and ... And yes, that somewhat negates what I'm saying, but you've got to make your assumptions somewhere. Those rectangles, the tolerance height, which way do we go? Where do we put most of our tolerance? Where do we put less of our tolerance? If you've got the facilities, well, of course, to do one versus the other, that's the sort of thing you do. Standard issue approach for most of this kind of mechanical, automotive size, aircraft size manufacture is we have tighter tolerances or smaller rectangles for the shafts than we do for the holes. Next semester, you'll be doing a subject called Design for Integration. You'll be designing a gearbox. And it's an industrial-sized gearbox, multi-ton, and it's essentially a reverse engineering problem associated with a gearbox on a container crane down at Port Melbourne. A guy called John, John, who used to own Deer Park Engineering, gave me this counter-argument. He deals with big stuff. Great big holes, great big shafts, and in his industry, container, crane, manufacture and delivery industry, he said that they often get the shafts standard, stock. They just come in from a third-party supplier, and that his workers, his factory workers, have to accommodate the shafts with the holes, so the holes that the shafts go in. So in that one, standard shaft sizes, we would be going with, I'll go a few slides. We would be going with a shaft basis fit, and that in John's factory, the hole is that which has to accommodate. You can't have a hole basis and a shaft basis, it's not going to work, unless you want right on that edge of transition. So, like I did, ask people, ask what their constraints are, and that helps with this process. And one more thing, and everyone learns this as they go, what are the range of manufacturing modes? What are the modes of manufacture that exist, and what are the modes of manufacture that are available? Now, I don't know if you do any manufacturing subjects in this course, other than a bit in this one, design for manufacture. So you wouldn't be expected at graduation to have a deep understanding of this stuff. That's the next phase for you as a new graduate if you move into that realm. Talked about that. Series of lathes. Now, let's get on to some of the things that I can actually ask you questions about. Wrong button, sorry. In the engineering world, when we're specifying a tolerance zone, this is the shorthand we use. Now, it's not literally 25K7. That top capital K and lowercase k corresponds to a hole and a shaft with a whole heap of stuff associated with it. 25 millimetres, I'll go from the bottom, is the basic size, as I've been talking about. It's the nominal size of a feature, and normally in millimetres. I'll look at the number next one over, that's 7. That's called the International Tolerance Grade. And that gives us an idea of the, if you like, the height of the rectangle. How high is the rectangle going to be? How small or large is the tolerance going to be? The smaller the height of that rectangle, the higher the tolerance, the more fancy and sophisticated has to be the manufacturing technique or techniques to get to that tolerance. And you might think, oh, where does that come from? That comes from a table. If I ask a question like this in the exam, that table will be in the exam. So it's good, being in this lecture, doing DP4 sets you up really nicely for the exam. And I tend to always ask a question or two of this sort of stuff. Just for, I don't know, build up your learning, build up your understanding of this particular shorthand. And then we've got the letter, the tolerance class. And this is where the tolerance zone is located relative to that 0 line, or the baseline, the basic size. And what we're getting at there is, I was saying about when we've got the base size, capital H0 or lowercase h0, where one of those tolerances are sitting right on that base dimension, in this case 25 millimetres, that's okay. But I never ask that kind of question. They're always a bit goofy and crazy. But that is practically a good way to go. Always have one of the 4 tolerance values associated with the rectangles for the tolerancing of the 2 components at the H value. And by the by, again, this corresponds to a chart, and it also has a lot to do with the application. Now, application is everything, and we'll get to another guideline on that in a second. Now, talked about this already. Uppercase letter corresponds to a hole, lowercase letter corresponds to a shaft. Now, if I gave a question of one of those 2 examples in an exam, I would not have to specify it's a hole or it's a shaft. Just there's enough information with those 3, enough information in that 25K7 for you to know what it is. So, I've got, I talked about how you can have all sorts of crazy stuff. 100P6, 40C8. This is a kind of shorthand that the engineer uses. Now, I've gone to the trouble to reproduce the table for our IT grade, or International Tolerance Grade, and I'm going to go forward a slide, and the example I'm going to look at is 8, capital M, 11. So there it is, just a whole heap of numbers. Tolerance value in micrometers, please always look up the units for the grade specified at the top of the column. Now that's the grade, IT6 to IT12, and the basic size is here. So we've got ranges of basic size. And one thing, it's less than or equal to. And, thank you for being in the room. Now, hopefully everyone in the room can see above, it'd be pretty goofy to have, at 0, it's a nonsense in terms of our geometric world. But once in a while, I'll ask a question where I'll actually have the number corresponding to, in this case, let's just say 3. Please, up to and including 3. So it's that row. It is not above 3, the next row. That's an easy way to lose marks, just by not being in this room, not remembering that simple, rule. Then, which do we choose? This is where engineering, after a bit of, I've just talked a little bit about cranking the handle, going through a process. Which of that IT number we choose gets a bit harder in practice, but I'll talk about that in a sec. But for now, the 8M11 is easy enough. 8 millimetres occurs between 6 and 10. 11 corresponds to IT11. And we haven't got an M yet, but we'll talk about that later. But the IT value is 90 micrometers. So we've got to start. That's the height of the tolerance zone. Just think about that M. I'll talk about it more in a sec. But here, and by the way, this is the standard I tend to grab stuff out of, AS 1654.1. You can also get values for sizes for large-scale objects greater than 500 millimetres. You might think, well, what's less than 6? Well, IT1 to IT5, there's numbers for them, but they're mostly for precision gauges, like that micrometer I was playing around with last time. The surfaces that come together on that micrometer and the tolerancing of the threads and all sorts of other things would be even more precise. That requires more sophisticated manufacture. And by the by, we can go the other way, IT13 to IT18. Just one more little note out of the standard. For sizes below 1 millimetre, you would never go for these more coarse, large tolerances. They don't make a lot of sense. And there it is. Now, in recent years, years ago, this subject had an open book exam. More recently, it's been closed book. The rise of social media has certainly played a big role in that. But this subject is not about memorising by and large. It's about understanding how to do stuff. And that's the chart that you will see in the back of your exam if there is a tolerance in question. Using it is what I'll be looking for. One more thing, micrometers, and then we get to a certain point, we go to millimetres. So 60 micrometers, 100 micrometers, or 0.1 millimetre at that dividing line. Always be aware of the units. So I did talk about how do we choose this IT value? Well, here we've got a lookup chart that you could make use of in the practical world. Everything is relative to IT6, and grinding offers a relative ratio of 1.0. So let's have a look. IT6 corresponds to 1. I could have got rid of the 0.0, but just 1. And we go lower IT values, higher IT values, and we've got some idea of process tolerance, and we've always got to think about the base size. Up there it's 25 millimetre, imagine a 25 millimetre shaft going into a lathe, and we're trying to just lathe it with a cutting tool, and then we're going to try and put it into some other machines to get a finer tolerance. So if we are going to grind, or they call it hone, that gives us a high quality fit. Tolerance grade IT6, we can get, they talk about 13 micron kind of precision. So 0.013 of a millimetre is the kind of tolerance range you can get with that. And you can see going upward to machine lapping, fine grinding, diamond turning, we get a higher tolerance. With grinding and lapping, higher tolerance again. But this chart, I hope, is indicating to you that trying to have a tolerance on an object, on any object, greater or lower, a tolerance, a smaller rectangle height than, say, 2.5 microns, to be blunt, would be goofy. I'm just showing you that very, very precise and expensive manufacturing processes get us down to about 2.5 micron. What is the, what is the application that you might assert needs to have a higher or tighter tolerance? Question, fantastic.
What's lapping?
I am not the manufacturing expert, but I'll do my best. You've got a plate, it rotates, and some goop, they've got diamond turning is, diamond encrusted something, it's like a diamond tip. When I did lapping, it was a bit of paste, and the guy says it's like toothpaste, but it's got fine, tiny particles of diamond in it. That gets slurped on the plate rotates, and then you put, often with specimens, when you put under a microscope, then you put the specimen on that plate as it rotates, and it, the diamond, that very fine material, essentially, like sandpaper, rubs it away, but because it's so fine, the particulate size is so fine, you've got this beautiful mirror finish, and the surface effect is not part of what you're observing under the microscope. That's the best answer I can offer. Is that good enough? Fantastic. By the by, any of these words, before this lecture I was having a look to see if there's anything worth, if someone had a YouTube kind of clip that just really gave some crackerjack good quality reports, and they were all okay, but they all took too long. So for everyone in the room, if you want to gain a bit of knowledge about any of those phrases and what they mean, just like I did, have a look on YouTube, and there's always someone talking about how they do it and what they reckon is best about it. What the common workshop, like our workshop, will be focusing on, we don't really even have grinding that I know of. We might, but I haven't seen anything. But certainly fine tuning is available. That's there. Broaching and honing. Now, I showed a broaching tool before. It's essentially just a nice, very precise tool, like a drill bit, but it just gets a more accurate hole produced. But it's not as good as this idea of grinding. And on we go. Lathe, turning, auto lathe, then we go into boring with a worn capstan. A capstan is the bit that holds the component that we're machining. And IT6 goes to IT7, IT8. So if you're just doing it on a standard machining operation, you get Octave to put a component onto his CNC machine, you could expect a IT7 kind of result. So you could ask Octave for 20 microns is 0.02 millimetres, 0.02, which is pretty precise, given that 0.05, 0.1 might be a reasonable range to ask Octave down the workshop, and he won't laugh, saying that's too hard, or we don't have the machines for that. They're the sorts of numbers that you think about as you go through that process. And on we go. All sorts of other, milling, slotting, planing, plenty of, I'm not going to examine you on any of this stuff. All I would really ever do is make you play cross-reference. Blah, 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 some process is underway, and there's a key word that you cross-reference back to this table and look for that word in terms of a manufacturing process and have a look about what tolerance grade that corresponds to. For the here and now, that's all I'd be asking for. For you wanting to become professional engineers and having a deeper understanding of some of this stuff, by all means. What else is worth commenting on there? We get right down to sand casting. So bells, great big valves. Sand itself is very coarse at that level. You can feel the grain size. So if that is the grain size that the molten metal is pushing up against, then it solidifies. Without subsequent machining, that's the surface effect. That's the surface we're going to get, and that's at the highest IT grade or the thickest tolerance. Cheap, but it has a very high tolerance. So it's not for precision manufacture. Certainly not for high strength, high speed, dynamic applications. I talked about M before, M for Margaret. M for Margaret sits just there in a whole basis set of tolerance classes. Now, all these cross-hatched rectangles are giving us a sense of how far away from our base size, before I was saying 25 millimetres, so this could be 25 millimetres base, and then if we have an M for Margaret as our next character, that gives us a sense of being here. So very close to the whole base. The upper limit in this case is very close to a limit. And for a hole, this is the zone on the left, higher than the base, is where we'd be thinking mostly about clearance fits. A bigger hole than the base, and the shaft is at the basic size, it'll fit together. On the other side, to the right, is where now we have to think about the hole, its smallest diameter, the maximum material condition, is less than the 25 mil, and then it's got the least material condition is even less again. Now that, in this case, let's go to the right-hand side. The least material condition we don't know, because we've got all these, it's an open rectangle all the way along. The IT grade that I've just talked about gives us how thick or how high each of those tolerances are. This, whatever letter value we're looking at, is merely looking at how far away from that zero line we want to be. And this is the standard. This is what engineers have used for many a year. What important feature? The H, so I talked about the base fit, that's H is right on the zero. And then, in this case, H, 0, and then IT gives us a least material condition. And that's something to think about. Any of this. Look, A up there, we've got a hole that is no smaller than that. So no smaller than what A is indicating would be our maximum material condition for a hole. There's more material to be taken away if we want to go up and up and up into that tolerance, to a least material condition. If we go down to the right-hand side, let's look at it just for the sake of it, Z. Z is you think about the material condition. We've drilled a hole. It's a maximum material condition because as we continue to take away more material, that's where we'll get to our least material left. Okay, it's not about how much you've taken away, it's how much is left. And that was the last thing I talked about in the last lecture. So that's for holes. And there's a bit more detail. I've focused there the H for you. We've got that's EI means the lower deviation. ES corresponds to the upper deviation. It swaps, as we go from on either side of the H value. We get that swapping effect. I will not ever really ask you sort of subtle questions about this J and JS stuff. It'll always be, give me a deviation diagram for a fit. And there'll be two rectangles that you'll have to produce, and then you'll be able to talk about how those rectangles come together, hole and shaft, to create a fit, and what kind of fit it will be. For the shaft, tolerancing, same essential process, except lowercase letters corresponding to, in this case, maximum material condition for A, and for a shaft up there, we've got our, let's make sure I get it right, Z, we've got our shaft, and our shaft can be bigger, so that's our least material condition for Z there. There can be more material added until we've got to that IT classification that we've chosen. And the red outline boxes are just giving an idea about just how many different, tolerance zones we've got. There's a plethora of opportunity. Some might argue too many. Sorry, back a slide. Too many. 486 tolerance zones for the shaft. So that's a lot. Same process as before. Lowercase h is what I always think is it's a happy tolerance to be given because one of the tolerance values for our tolerance rectangles is 0. We've only got to work out 3, adjacent or adjunct numbers associated with the IT value for the shaft and then 2 finite values for the hole. And as I've said, J and JS is not something I'll examine you on, but it's in the standard. Copy of the standards on the LMS website if you're interested. So, and this is it is a payoff for the mathematically inclined. With what I've talked about thus far, with these the IT values and these classes of size, we, the engineer, can provide ourselves with up to about 470,000 different tolerances, more than we'd ever need. And so that's part of the power of this whole discipline. However, it's only of any real value to have that many combination of fits if we're able to get some kind of optimised outcome for the circumstance we're working in. And after the sort of the big picture, let's bring it back to something that's more readily interpreted by the engineer. Now this is out of ANSIB 4.2. It's not a standard but merely guideline, and it gives preferred fits. Now these things are like gold. What's up on the screen now? On the left-hand column, for a series of different clearance opportunities, we've got loose running fit, free running fit, close running fit, sliding fit, locational clearance fit. What does that even mean? Well, there's some more words to help with the kind of fit you or we, the engineer, might be looking for. And nicely, we've got both hole and shaft base fit opportunities. And note, lots of capital H's and lots of lowercase h's. And interestingly, we've got one of these right on the edge of a transition fit with a H7 and an H6 and an H7 and an H6. So we run the risk, just like the component that Bill made for me, where I can actually just get them to slide together and very tightly slide together. It's written up there, snug fit. Can be assembled or disassembled, etc. Now I do have highlighted a couple. This second from the top is good for keyed shaft and pulleys. Third from the top is good for pistons and cylinders. So, you know, automotive, piston and cylinder, and if you see an H8F7 or an F8H7, notice just the reversing of values, well then you see that, you can say, okay, sorry, back we go. You could think, okay, the sort of thing that we could use for piston and cylinders. Here's a transition. Again, this top one could be a key and a shaft. More accurate location where greater interference is permissible. Some things, things like a bearing on a shaft is, we do want transition to interference and we do want precision. So this kind of transition fit is, a bearing on a shaft is another example, instead of just a key in a shaft. And a key and a keyway, I showed an image of that before. A key is just a rectangular solid lump of material, slot in the shaft, slot in the gear wheel or the pulley belt wheel, and the key provides torque transmission between them. But we can't, of course, have the key rattling around inside that slot. So we do want a precise fit of the type that I played around with. Snug transition type fit. For interference fits, I won't go through the same process. You can see it's all there. The words are there. You've got, I think it's clean. No, there isn't a clean. Sorry, there isn't a clean version of this. Perhaps I should get rid of rail wheel on wheel for the first version. But again, the worst you'll have to deal with in this subject is having to refer to the words to a symbol. That's it. And a forced fit is an example of which is a rail wheel being pushed onto an axle. And I talked a bit about that in the last set of lectures when I was looking at pushing Peter McGowan, one of his case studies. So for parts which can be highly stressed and for shrink fits, that temperature differential, the hole gets hot is made hot, the shaft is made cold, they put them together while the temperature differential exists, temperatures normalise and we expand and contract and get a forced fit. Railway wheels work that way. Now, here's the kind of chart that AS 1654 way back in 1974 used to use. I'll give you a look at that. A few nice features on this. One is the cross-hatched hole with a H0, so it's got a whole base feature with a whole heap of shaft sizes from very high tolerance getting smaller and smaller tolerance, or IT value, as we move along. So that's C11, D10, I can't see that, F7, it's like the optometrist. We get to H6 over on the right and H7 up top. Now this is up to 500 millimetres diameter. Down the bottom there, I've got in orange, from 0 to 500. The two columns on the left, as per what I did before, don't forget above and up to and including. And then all this zone, and you can't see it here and now, but all the numbers inside each of those cells gives us, easily, we don't have to do any interpreting, the size or height of the tolerance zone, which is a rather nice thing. And this is for the hole-based fit. For transition fits, by the way, the arrow, back I go a slide, that arrow over there is just indicating this. When I scanned this, I couldn't fit it all on the image, so I've just put a bit more on. We've got into transition, where the hole-based fit is there, and we've got our shaft and hole being in the same kind of zone, in its tolerance zone, there as well. And then as we get to the last two columns, the shaft is the hole is as it was, and the shaft diameter is always bigger. No matter where within that statistical range or the normal distribution range, the shaft is always going to be bigger. And so that's the interference fit end of things. That enables us to produce a roughly or reasonably scaled diagram, because these ones are reasonably scaled in a way that gives the reader, viewer, a snapshot of what's going on. That, by the by, we would regard as on the left, a rather coarse clearance or lots of clearance, sloppy clearance. They're the kinds of things we'd be thinking about. As we move to the right of this chart, we're getting tighter tolerancing, maybe more high precision, maybe more high performance applications. Now, this is the more recent version of the same thing. Basic size, and I've put this one up, and this is, by the way, 1995. I will always use the 1995 one, the more recent edition. We haven't had any new editions since. And we've got, as I've indicated before, micrometers, but then as we get into larger sizes, H for basic size, up to 12 and above, we're looking at millimetres. The other thing I want to point out is there's a couple of blank spots up there. What does the engineer do if there's nothing in the cell that you're looking for? And that's all over the place in the actual standard. And I've scanned, by the way, I've scanned this standard, and that's up on the LMS site for you to have a look at as well. And once in a while, when I'm feeling particularly cheeky, I will indicate something like, 2mm H17. And you will go there and you think, Colin, you made a mistake, there's nothing in the cell. And I say, well, it exists. I can quote you the idea. Just because there's nothing in the cell doesn't mean it's not you can't solve the problem. You're an engineer. And I'll give you the answer. You'll go to the previous one where there is a number. You'll interpolate back and look at what's changing. That's all I'd ever expect. That's all any manager would expect. If someone's giving you something goofy outside of an academic context, the learning is, well, I'll just use something that's reasonable and plausible and appropriate near it. Here and now, I'm doing it on purpose. In the real world, it would be a goofy thing. You wouldn't expect a specified value that had a blank cell in the associated Australian standard. Almost done for the day. And here we've got the same essential chart, but in this time, limit deviations for the shafts of base lowercase h. And if you look through that chart, you'll see lots of zeros all the way through it. So these charts, or these tables, are essentially putting in longhand form the IT value and the capital letter distance from the basic line value for all a huge range of potential tolerances. So I want to try and finish off with this quick example. Draw a deviation diagram for 40mm D7N8. None of these have a hole basis or a shaft basis, but we can readily solve it. From table 3 in the 1995 edition, D7, we've got a couple of values. N8, we've got a couple of values from two distinct tables in the standard, table 3 and table 25. So D7, N8, we've got for the value of 40, which is between 30 and 50. both times, trust me. We've already got the 4 values we need. Now, you can also go through this process of looking up IT7 from that earlier table, and that has a hole tolerance of 25 microns. So we can also go with the deviation. The D7 has an upper deviation limit of 80 plus 25. That agrees with the table 3. N8, we can do the same process. IT8, it should be 56 minus 17 equals 39. And I can prompt 56 minus 17 over there, and that should be 39. And I can promise you that it is. This is why these questions should be the easy questions in your assignment DP4 or the exam, because you can check your answers with this simple process. And there it is there, IT839. And this is a good point to stop. That's what we're after. That's the deviation diagram. And I know the overlap doesn't mean anything. I just did it that way so I could fit everything in nicely. 80, 105, 57, 17. All I would ask is that 80 is higher than the 57. Excuse me, voice is going. And that 17, of course it's plus, it has to be higher than the 0 or baseline of 40 millimetre diameter. There's more to come on this, but that'll do for today. Thank you for your attention, and see you next time.